Okay, good. Thanks for the introduction. I hope you can see my screen. You never know from my side. And okay, so yes, thank you for the introduction. Thank you for inviting me to talk at FHE.org. And I'll be talking about homomorphic encryption. So I guess to this audience, FHE is not something that needs much of an introduction, but as the talk is being recorded, let me briefly recall how encryption typically is used to secure information for storage or transmission. And homomorphic encryption is as an enhanced form of encryption that allows to perform computations on encrypted data. So that, for example, you can encrypt your data, put it on a remote server, then perform computations on it in encrypted form, retrieve the encrypted result, and finally decrypt it using your secret key. Now, just to put this into context, historical context, the concept of FHE was initially introduced in 1978 by Rivest, Adelman, and Dertuzos, who posed the problem, but without offering a concrete solution. And a major breakthrough in the field happened in 2009 when Craig Gentry convinced the world, the cryptographic community, that the problem could indeed be solved by proposing a first candidate solution to the problem, and perhaps even more importantly, introducing a bootstrapping technique that ended up serving as the backbone, as a central tool for all subsequent constructions of FHE. Now, another major step was taken in 2011 when Brakersky and Vaikunthanathan proposed what today is considered the first solid solution to homomorphic encryption based on the standard lattice problems. And many other schemes were proposed since then, but one common feature of all the non-FHE schemes, or at least most of them, is that they are all based on lattices, and they make use of this bootstrapping technique originally introduced in 2009. Now, many other schemes were proposed since then, schemes that are often grouped into categories or generations, and there are different ways to do this, but one way which I think is conceptually useful is to group the schemes based on how they perform multiplication. And the first generation of encryption schemes, starting with the schemes of Brakersky and Vaikunthanathan and the BGV scheme with Gentry and variants, performed multiplication by tensoring. So taking tensor products was key to perform multiplication. And then a second generation started with the GSW scheme of Gentry, Sahai, and Waters that introduced a completely different method to multiply ciphertexts. Now, there are a few variants of these schemes, but I didn't really put much here. There were very few variants of GSW. The scheme, as originally proposed, already had a number of very useful features. And some of these features were used just as a technical tool to build one more, a third generation of schemes that started with a scheme proposed by Duca and myself in 2015, that using GSW just as an internal building block to perform bootstrapping, proposed a different method to perform fully homomorphic encryption that uses a very simple scheme, like a standard LWE-based encryption scheme supporting only addition, and then it gets to fully homomorphic encryption by combining that with what we may call a functional bootstrapping operation, an operation that during bootstrapping, which I will describe soon, can not just compute identity function, but it can compute an arbitrary function, or at least a random function, which is used to go from just additive homomorphism to something that allows to perform arbitrary computations. And there have been several variants of this scheme. A few, most notably, is the variant over the torus, TFHE, that has been receiving a lot of attention also because it has a well-developed library and allows to perform operations in a way that at the high level is essentially the same as FHE, but with some optimized algorithms for bootstrapping and other operations. So the schemes that I will be focusing on in this talk are essentially FHE, so this third generation method to perform encryption, and CFHE, a different method that sometimes is put as a different category on its own because it is approximate, and I'm putting here in the first generation because it is still using multiplication by tensoring, but we will see how approximation is something that can make a big difference. So I will not talk about any specific encryption scheme. This presentation today will be more high level, conceptual, on what are the abstract properties of these schemes, but FHE and CFHE are the two most representative schemes for what I'll be talking about. So specifically, my talk will be centered more around the abstract definition of what it means for a scheme to be fully homomorphic. And I will start with a traditional definition of homomorphic encryption scheme. And then I will very briefly talk about lattice-based encryption, but just to show how lattice encryption is inherently noisy, and performing computation increases the noise of the ciphertext and leads to bootstrapping as a technique to reduce the noise in the ciphertext and keep computing. But the real core of the talk will be a different definition of homomorphic encryption. Is something that I like to call fully composable homomorphic encryption, or if you prefer, composable FHE. And it gives a different perspective on bootstrapping, which I think is at the same time both enlightening and also very simple, to the point that I will give full proofs. So don't be scared. So this will be very easy, but I will basically show you formally how to achieve this strong notion of composability, which has many nice features. And finally, time permitting, I will talk about the approximate encryption, which extends the definition of homomorphic encryption, but in a different direction. So, okay, so I assume that we started a little bit late, some 12 minutes late, so I will take some extra time at the end. But in case there is some other event right after this that cannot wait, the host can please interrupt me, and you can stop me before we get to the approximate encryption. Okay, so encryption schemes. So you're all familiar with encryption. It has a very simple syntax consisting of a key generation algorithm, gen, an encryption algorithm, and a decryption algorithm. And the correctness property of a standard encryption scheme is that after generating a pair of keys, a public key and a secret key, and then you take a message, you encrypt it to get a ciphertext C, and then you apply the decryption function to get back a message M, you will get exactly the same message M you started from. So this is the standard correctness requirement for encryption. And the standard method to define fully homomorphic encryption is the following. First, we extend the syntax of a homomorphic encryption scheme with an evaluation algorithm, eval. And then we extend the correctness requirement as follows. So the evaluation algorithm takes as input not only a ciphertext, but also a function, f. And the scheme should have the following property. If you take a message M and you encrypt it, then you apply the evaluation function, you evaluate F homomorphically on this ciphertext, and then you decrypt the result of the evaluation. you will get exactly the same value as what you would obtain by performing the computation in the clear, taking your message M and computing the function F directly on M without performing any type of encryption. So we have these two paths in the pictures. You can either go directly from M to F of M, or you can go up to a ciphertext, evaluate, and then decrypt. And these two paths should give exactly the same result. So you may say that this diagram should commute. Now, this is a good definition. It well captures the intended use of homomorphic encryption schemes, which is to store your information in encrypted form, perform computation on it, and then decrypting the final result, and use this process to secure the process of computing the function F directly on your data. Okay, so lattices. So I'll be very brief here, assuming some familiarity with lattice cryptography, as you have already seen many talks involving lattices today. And in a lattice encryption scheme, typically the secret key is a vector with integer and often small coordinates, S, and a message M is encrypted as follows. The encryption algorithm picks a random matrix A with uniformly random entries in some finite ring, for example, the integers modulo Q. And it also picks a random noise vector E. And by noise, what I mean is that the coordinates of E are small. In particular, they are less than delta over 2, where delta is some scaling factor. And the message M is encrypted as AS plus a scale copy of the message, delta M, perturbed with this error vector E. And this second quantity is what I call B here. And this ciphertext can be decrypted simply by subtracting AS from B. Now, if you remove AS from B, you are left with M delta plus E. And if you divide this expression by delta, you will have M with a perturbation equal to E over delta. And that's why if delta is less than, if E, the error, is less than delta over 2, then you can simply round this value to the closest integer and recover the message M exactly. And this establishes the correctness property of lattice-based encryption. Now, naturally, this scheme satisfies a very interesting homomorphic property. It is linearly homomorphic. If you add up to ciphertext, C0 encrypting M0 and C1 encrypting M1, now ciphertexts are matrices, so addition is just addition of matrices. And if you add them up, you will see that if you factor out S and delta, the final result is an encryption of the sum of the two input messages, M0 plus M1, with an error which is also the sum of the two input errors. So if the input errors are less than delta over 4, the final result will have an error which is less than delta over 2 and can be decrypted. Now, this is great. We have a valid encryption of M0 plus M1, but it is clear, even from this simple example, that this homomorphic property has some serious limitations. You cannot keep adding things together. The error will get bigger and bigger, and at some point you will get a ciphertext which is not decryptable. Now, this is where gentry bootstrapping technique comes into play. So this is a technique to reduce the amount of error in a ciphertext, and it is done as follows. So it assumes that the scheme supports the evaluation of its own decryption function, but with a twist. So typically the decryption function is seen as a function described by a secret key that takes as input a ciphertext. So here we flip the role of the two inputs. We want to think of C as the description of the function, and the secret key, SK, as the input to the function. Next, since we cannot reveal the secret key, we encrypt it, and we publish the encryption of the secret key, and the evaluation function is computed by applying this function FC on the evaluation key, on the encryption of the secret key. And if you just do your math, you will see that this is still a decryption of C. So it is an encryption of the original message. So this is a very simple, I would say trivial, almost trivial evaluation. It is evaluating the identity function on a ciphertext without changing the ciphertext at all. But it has the nice feature of clearing the noise from the ciphertext C. Since we think of C as the description of the function and EK as the actual input, the noise of the final result, C prime, will depend on the noise of the EK, while the original noise that was in the ciphertext C gets decrypted away, disappears, and if you set up the parameters properly, you will end up with a ciphertext C prime that has a level of noise which is smaller than the original ciphertext C, which allows you to keep computing. Now, it is also clear from this brief description that this solution requires the encryption scheme to be circular secure. That is, it should support the secure encryption of its own secret key, which gets encrypted and published. Now, so this circular security has been essentially a core open problem since the early days, since the first proposal by Gentry and then the first proposals based on LWE and standard lattice assumptions. Bootstrapping has been used to reduce the amount of noise in lattice-based ciphertext, and bootstrapping has been implemented using circular security. So the question of whether the circular security assumption can be made without loss of generality has received quite a bit of attention. And in a sequence of papers, it has been shown that at least for standard encryption, not for homomorphic one, it has been shown that there is no black box construction from a standard encryption scheme to a standard encryption scheme which is circularly secure. So it seems to be an added assumption that may or may not be satisfied by your scheme. And most likely this black box result can be easily extended to homomorphic encryption schemes. But for sure they were motivated in good part by the homomorphic encryption problem and the bootstrapping technique. Now, another possibility to address this is whether one can prove circular security directly from the LWE problem, but again, a question that has remained open for quite a long time. So what I want to do in this talk is to present a different perspective on bootstrapping and the design of homomorphic encryption that does not directly involve circular security. I mean, circular security will come up again as a possible technique to solve the problem, but is not necessary to ask some interesting questions. And to get there, let me first bring your attention to the problem of composition. So assume an arbitrary, not necessarily lattice-based homomorphic encryption scheme that allows for the computation of a wide class of functions. So there are, say, two functions, f and g, which can both be individually computed on ciphertexts, satisfying the traditional correctness definition. Now, what happens if we want to perform the two computations in sequence? That is, first we apply f to m, and then we apply g to the result to get g of f of m. And we want to perform this homomorphically on encrypted data. So we start by encrypting the message m into a ciphertext C0. Then we evaluate the function f homomorphically on C0 to compute a ciphertext C1. Finally, we evaluate the function g homomorphically on C1 to get one more ciphertext C2, and we decrypt this final result. And the question is this ciphertext C2 something that decrypts to g of f of m? And if you look at the specific solutions to homomorphic encryption schemes, you'll see that the answer typically is no, that doesn't quite work. It's something you would like to have, but is not necessarily true. And the reason this is not true is that the definition of homomorphic encryption scheme that I described before, the traditional definition, is not composable. In particular, if you, so we know that this message M can be encrypted, evaluated, and decrypted to give f of m. We also know that if you encrypt f of m, evaluate G, and decrypt, you will get G of f of m. Now, these two diagrams are individually correct. However, the output guarantee of the first diagram does not match the input requirement of the second diagram. All we know is that C1 decrypts to f of m, while for the second diagram to be applicable, we need C1 to be the result of applying the encryption algorithm to f of m. Now, these two things may seem almost the same, but they are quite different. And it's easy to see that the two properties, property 1, C1 is an encryption of M1, and property 2, C1 decrypts to M1, one of them implies the other one. And that's because if you take a message M, you encrypt it and then decrypt it, from the correctness properties, you will get the final result of decryption will be equal to the original message. However, if you perform the two operations in the other order, you take any ciphertext C, decrypt it to get a message M, and then you encrypt the final result, you will typically get a different ciphertext, if not just for the fact that encryption is a randomized process. So it's unlikely to give you the same ciphertext twice. Now, in the context of lattice-based encryption, there are other reasons and intuitive justifications why we don't expect these to compose and compose arbitrarily, which is that the noise of the ciphertext gets bigger and bigger and bigger. But if you look at this picture, you will see that this problem with composition is not something specific to noise, is not something specific to lattices, but it can be attributed to the specific way that the correctness is defined for homomorphic encryption. As an abstract cryptographic definition, this definition of homomorphism is not composable. Now, this leads to a different definition, what I like to call fully composable homomorphic encryption, which is very similar to the previous one, but with a twist. So the difference is that instead of starting from a message, encrypting, evaluating, and decrypting, what we do is to start from a ciphertext C. And we require that for any ciphertext C, if you decrypt it, and then you apply a function f in the clear on the result of the decryption, you should get exactly the same result as first evaluating the function f homomorphically and then decrypting the result of the evaluation. So in a sense, evaluation and decryption should commute, these two operations. Now, this is a different definition as what is typically given. So let's compare these side by side. So in the traditional definition, we start from a message and we encrypt, evaluate, and decrypt. And this should give the remaining edge in this commutative square. In this newly proposed definition, composable FHE, or fully composable homomorphic encryption, we have that we go from the upper left corner to the lower right corner of this diagram, and we can either perform first decryption and then evaluation, or first evaluation and then decryption, and we require these two processes to lead to the same result. Now, the nice feature of this definition is that, as it can be easily seen, it composes very nicely. It is fully composable, and that's why, and that's because the output guarantees of this definition, C1 decrypts to f of m, is precisely the input requirement of the definition. If C1 decrypts to f of m, then you know that evaluating function g and then decrypting gives the same result as first decrypting to get f of m and then applying the function g. And we know that decrypting C1 gives f of m as a result from the first diagram. So we get a fully composable definition, which is very appealing because it allows to design encryption schemes that rather than directly supporting arbitrary complex functions, we can focus on a small set of operations. And this was the main innovation taken by the few scheme, focusing on very small operations, but in a fully composable way. And instead of thinking of the encryption scheme as being able to evaluate arbitrary programs, we can think of it as a method to evaluate in a fully composable way the basic instruction set of a general purpose programming language, and then the programs can be put together just using composability, one instruction at a time. But it allows to focus the process of designing the scheme on very small operations, leading to schemes that are more efficient, at least when you look at the evaluation of single instructions. Much smaller ciphertexts and much shorter running times. Now, it's easy to see that the composable definition implies the traditional one, and here is a proof, but let me just skip this. So you can work it out by yourself just using the equations of the two correctness properties. The problem I want to talk about is the opposite direction. So from a composable FHE, so any composable FHE is by itself a traditional FHE scheme. So I want to ask if an FHE scheme can be transformed into a fully composable one. Is it possible to take a scheme satisfying the weaker definition and transform it into a possibly different, a slightly different scheme that is fully composable? Now, this gives a different way to look at the bootstrapping operation. So I will show you that the bootstrapping solves this precisely this problem. You can reinterpret Gentry's bootstrapping theorem as a proof that if you have an FHE scheme, non-composable FHE scheme, which is also circular secure, then you can transform it in a black box way into a composable FHE scheme. So we start from an FHE scheme here in black with a key generation, encryption, decryption, and evaluation algorithm. We'll build a different scheme in red, the CFHE scheme, which is going to use the same encryption and decryption functions. I'm only going to change the key generation and, importantly, the evaluation algorithm in red in this picture. So, let's look at what we want. What is the goal? So we have a ciphertext C, and we have a function f that we want to evaluate homomorphically on the ciphertext C. And we know that if you decrypt this ciphertext and then apply the function f, you will get a certain value, f of the decryption of C. And the goal is to find some other ciphertext C prime that has the property of decrypting to f of the decryption of C. So we know the output to the decryption function. We want to find a corresponding ciphertext that can be given as input. And this ciphertext C prime should be precisely the output of this new evaluation function which are about to define. So how can we find such a ciphertext C prime that decrypts to the correct value? Well, we assume that the original scheme is circular secure. So something that we can do for sure is to take our secret key and encrypt it. And so I will call this EK, evaluation key, because I will use this value, this key, as the evaluation key of the evaluation function of the new scheme. So I will use this ciphertext, which is secure. It can be made public because the scheme is assumed to be circular secure. And we want now to define how this evaluation function operates on an input ciphertext C to produce a ciphertext C prime. Now remember, what we want from C prime is to decrypt to a certain value, which we know how to compute. So how can we get a ciphertext with a certain decryption property? So we want to get this orange commutative diagram here, but all we have is a different type of encryption, one with a property that if you encrypt, evaluate, and decrypt, you get the same result as performing your function in the clear. But this gives us a way to find a ciphertext C prime that decrypts to what we want. Just take a function that maps this value, this secret key, maps to what we want. We encrypt it, then we evaluate this function homomorphically and then we decrypt it, and we know that the final result will be exactly this value from the non-composable properties of the original FHE scheme we started from. So if we take the upper left corner of this diagram, we'll get a ciphertext C prime that decrypts precisely to what we want. So what function shall we have here? A function G that maps SK to the desired output. So is a function G that maps SK to F of the decryption under key SK of C. And importantly here, we think of SK as the input to the function and C as part of the function description, so that we can apply this commuting diagram. So at this point, we're almost done. All we have to do is to evaluate this function G homomorphically to go from EK to the evaluation of this function G on EK, and by construction we got a value that decrypts to what we want, and giving an evaluation algorithm that has these fully composable properties. So we can define the evaluation algorithm in red as using EK as a key, function F and ciphertext C as input, and producing the ciphertext C prime, obtaining by running the previous, the old evaluation function on this function G that we just defined, and the evaluation key as input ciphertext. Now notice how this picture is using bootstrapping, is using circular security to get a composability property. There is no mention of noise. There is no mention of ciphertext having a noise that is getting bigger and bigger, and the need to do bootstrapping to reduce the noise in the ciphertext. So we are using this same technique to strengthen the properties of our scheme and achieve a stronger definition of fully homomorphic encryption, in particular the fully composable homomorphic encryption. At this point, we can ask a number of interesting questions. Notice that while we use the circular security in transforming one scheme into the other one, the two definitions make no mention of circular security. They're just the properties of composition. So one may ask if FHE implies a composable FHE even without using circular security. That is there a transformation that given an FHE scheme, is there a way to build a new composable FHE scheme and prove it secure? And notice circular security is something that I used in the previous slide as a way to show how Gentry's bootstrapping can be seen as a solution to this problem, assuming circular security, but there is no requirement or expectation that any of these schemes is circular secure. In particular, the original scheme may not be circular secure. The final scheme may not be circular secure. In fact, it's probably very easy to modify the output scheme so that the result of the construction is not circular secure. So finding such a general construction would allow to base fully homomorphic encryption on standard lattice assumptions without the need for the additional circular security requirement. But of course, maybe the answer is no. But in that case, it would be good to get some better understanding of the situation. In particular, one may ask, it is possible to prove that you cannot do this generically. There is no black box construction from fully homomorphic encryption to composable fully homomorphic encryption. So there is no generic transformation. Any transformation needs to use the specific properties of the scheme. Another possibility is to show that the only way to do this transformation is to use circular security in some technical sense. In particular, is it possible to show that if there is a generic transformation from FHE to composable FHE, then necessarily you can also build FHE schemes which are circular secure. And that would again provide some understanding of why after 10, 12, 13 years since the first FHE scheme, we are still making these circular security assumptions. So far so good for the problem of defining composability, and now it is 8:45. That was the official end time of the talk. If I can use the 12 minutes missing from the beginning, I will go on and talk about this, but let me ask to my host if it's okay to go on. Should I go on?
Yeah, you can go. Yeah.
Okay, good. Okay. Okay, good, thanks. Okay, so it won't take long, it will be 10 minutes. So yeah, you won't be late for, I think the next event is a social one. I'm sorry I will be missing it, but I'll, yeah. If you leave the Zoom on, perhaps I can watch you having fun. Okay, so let's get to approximate encryption schemes. So this is a different way to extend the definition. In this case, we are weakening the definition rather than strengthening it. And in a standard scheme, the definition is that if you take a message M, you encrypt it and then decrypt it, you may not get the original value. You may get a perturbed value, M plus epsilon for some small value M. Now you may ask, why do you want to do that when we know how to do exact encryption? And the primary motivation is that you can gain in efficiency. There are homomorphic encryption schemes that are approximate and can perform homomorphic computations more efficiently than standard ones. And the definition for homomorphic encryption, at least the traditional one, here I mean, you can also think of combining approximate, fully composable homomorphic encryption, but it gets trickier because you also get these approximation errors that add up in the process. So just focusing on the traditional definition. So this is extended or weakened as follows. If you take a message M, you encrypt it, evaluate a function f homomorphically, and then decrypt the result, you will not get f of m, but you will get something close to it. You will get f of m plus epsilon. Now, the approximate encryption scheme was put forward by the CKKS paper by Cheon et al. That showed how using approximation you can gain in efficiency. And this efficiency comes from the fact that lattice encryption is performing some form of error correction on the message, take the message M and scaling it by a factor delta in order to correct the error in the end. Now, if you remove this factor delta completely, CKKS does something slightly different. There is still a factor, but is somewhere, and it is also called delta, but for a different purpose, for the purpose of using floating point numbers rather than just integers. So the encryption is simply removing this delta, and in some sense it is very similar to the first generation schemes, but without this error correction scaling factor. And if you decrypt, when you subtract AS from B, you will get M plus the error, and you can simply leave the error there and think of it as a perturbation that gives an approximate result. Now, this removing the delta seems it doesn't really change the complexity of encryption of decryption by much, but it has a big impact on the error growth in homomorphic computation, which ends up being very important in applications like machine learning on encrypted data, where it's okay to have approximate results. Even the input is approximate when you take real world data, and you can get a substantial efficiency boost in practice. Now, both schemes are secure at face value. If so, they are both based on Regev learning with errors problem that says that an expression of the form AS plus E is pseudo-random, is indistinguishable from a pair where the second value, B, is chosen uniformly at random. Now, if you have something which is random and then you add something to it, be it M or be it delta of M, delta times M, you will still get something which is uniformly random. So it follows from the pseudo-randomness of the LWE problem that both schemes have the property of producing ciphertexts which are indistinguishable from random strings, which would seem at first to protect all the information that you need to protect about the original message. So is this enough to build a secure LWA encryption scheme? Now, this turns out to be enough for the standard notion of encryption, but it is quite problematic for approximate encryption, and this is easily illustrated with the following example. Think of having a data set X on which you want to perform some secure computation. You want to compute some statistics on the encryption of X. You can first encrypt all the values. You encrypt X1, X2, X3, all the way to Xn. Then you can add up the results in encrypted form. And then at the end, you can decrypt the result of this homomorphic addition to get a value X prime, which is close to, but not identical to X, the actual sum of all the input values. Now, assume that you encrypted these values because at the time when you published your statistics, this data was considered sensitive, but perhaps the data is not sensitive anymore. Maybe after a certain amount of time, it can be publicly revealed. So you reveal your data set and you put it in the clear. It's not a security problem anymore. And so it turns out, and this is what we showed last year at Eurocrypt in a paper with my student, former student now, Bayu Lee, we showed that just the fact that these two values are different, X and X prime, opens the door to some serious attacks. Given the difference between X and X prime, it is possible to recover the secret key of the scheme. So the fact that the result is approximate leaks information about the key. Now, this is very bad. This is a serious problem because while this input set X perhaps was not sensitive anymore at the time you are publishing it, perhaps this same key was also used to encrypt other data sets. And the fact that you can recover the secret key will completely break the security of all the other applications that were making use of this scheme. So in order to address this, one needs a stronger definition of security than just the indistinguishability of ciphertext. And this is something that we defined in this paper at Eurocrypt last year, highlighting the security weaknesses, showing that the schemes as typically implemented can be attacked. And we gave a definition that, a new definition that involves an attacker that has a limited access to a decryption oracle so that he can get to see the result of approximate decryptions. It's something very different from CCA security. It's not an active attack, it's still a passive attack, but it is the right way to formalize passive attacks against approximate encryption schemes. And so in that paper, we suggested some practical countermeasures, but without solid solutions. And so we have a new paper to appear at Crypto, at the next Crypto, and also soon to appear on ePrint, where with Bayu and my other students, Mark Schultz and Jessica Sorrell, so we showed how to provably achieve this extended notion of of security for approximate homomorphic encryption schemes. And we show how to achieve it with a relatively modest amount of additional error using techniques from differential privacy. Now, let me conclude with the questions. So the title of my talk was definitions and questions. So for the composability, the question was, can we get an understanding of the relation between these two different definitions, the traditional definition of FHE and composable definition, the fully composable homomorphic encryption. So here you can ask a similar question. Oh, can you go from approximate FHE to standard FHE. But if you formulate this way, the answer is very simple. Yes, you can do it. You just combine encryption with some form of error correction. You correct from the error and you get the exact result. Now, the interesting question is, how does this impact the efficiency of the schemes? In particular, while the potential efficiency advantages of approximate encryption have been clearly demonstrated on specific example applications, showing that, oh, you can do learning on this type of functions with so many attributes, with so many this and that, and the numbers are bigger than what was possible to do before on specific problem instances. I don't think that at this point we can really say that we have a good understanding of what is this bind to us theoretically. So is there a possibility that, yes, approximate homomorphic encryption can be transformed into exact fully homomorphic encryption, but only in a way that has a substantial cost? And the question is, how should this cost to be formulated to make sense theoretically, asymptotically? So I don't know, perhaps the result is going to be the opposite. There is a way to transform approximate homomorphic encryption, not specific to lattices in general. Is there a way to remove the approximation in a way that has no impact on the asymptotic theoretical efficiency of the schemes, and it's just for practical instances that we can gain a little bit using approximations? Or is there a fundamental theoretical gap between these two notions that shows up in terms of efficiency? So getting a good theoretical formulation of the efficiency gap between these two notions, I think, is something that it would be good if it received some attention. It could improve our understanding of what can or cannot be done in practice. And this concludes my talk. Thank you for your attention.